Third up today is Ben Stafford. I know Ben is here. There you are.
Hello, I'm here.
And Ben worked with two different mentors this year, Gwen and Mohammed. I think I see both of them here. So if you all would like to introduce Ben, we can get started.
Can you hear me well?
Yes.
Hello, thanks so much. Ben Stafford has been a senior high school student, and he graduated with the excellent honors degree of 97 out of 100 GPA. He is also an intern of Rochester Institute of Technology to computer engineering. His passion is doing circuits, electronics, and his mind is into developing procedures for a better calculation and in terms of programming as well as electronics. He has worked, he did a very good job and hard work on so-called time of flight compartment of the electrostatic analyzers with me, Mohammed, and Gwen. That we are based in the Space Science Laboratory of University of California, Berkeley. Thanks.
All right. And Ben, you have your own slides, is that right?
Yes, just one moment while I get it ready.
Go for it.
Okay. All right. Can you see that?
Yes.
All right, I'm going to be presenting Understanding and Simulating the Time of Flight Analyzer by me, featuring Gwen and Mohammed as my mentors. So the motivation behind the whole project is to understand the composition of plasmas in space and the various masses of different species, and that any planet with an atmosphere has an ionosphere, so it interacts with solar wind and has important effects on the planet and how its atmosphere is evolved over time. So the goal of this research is to determine what the ionosphere is made of and its importance of the different species, and also to make the sensor easy to construct and improve its design. So we want to make it as cheap and low cost as possible so NASA can build it easily. So here are the variables we're going to be using throughout the presentation. The main ones that we're going to be focusing on today are the ESA, which is energy from electrostatic analyzer measured in kiloelectron volts with the unit keV. Energy and time and mass. We're actually solving for mass, so that's an important one. Of course, mass is measured in grams, and the rest are measured in standard metric units. So here's an introduction to the diagram that we'll be studying today. So you notice here on the left, we have our distance variable. This can be any 2 points, the distance between the two. Of course, NASA built the analyzer, so we know what the distance of any 2 points is. So you can see here, I just have an example of this distance here. Each of these ticks is about a millimeter. So you can use a ruler or whatever to measure this and get the measurement value out of it. So here at the top, you'll see ions. This is where the ions come in, and I'll talk about more of this later on. Electrons are flowing this way and also down right here. Neutrals are these lines right here. Neutrals have no charge, so they're not attracted to any surface. Right here at the bottom, you can see this is detector number 1. This clock is signifying a timer, and this is the start timer. So when the electrons hit this plate here, the timer is started. Whenever the electrons come down to this point and hit this plate, the timer stops. So the difference between the stop time and the start time is going to be our t, which is measured in seconds. And of course, these circled surfaces here are charged with a specific amount specified in the simulation, which we'll get to at the end. So here's the proof of our equation. You can see here we start with the base equation, E equals 1/2 mv squared, which is energy equals 1/2 mass times velocity squared. So we are going to solve this in respect to m, which is mass. That's the whole point of the research, is to understand the mass of these particles. So first off, to do this, we're going to multiply by 2 on both sides. So now we have 2 times E equals mass times velocity squared. So by multiplying this by 2, we have gotten rid of this fraction. It is now 1, because 1/2 times 2 is 1. So it is understood to be 1 here, which is why we're not showing it anymore. Continuing on, now we divide by velocity squared on both sides. You can see here we are doing that. And at the end here, we get 2 times energy over velocity squared equals mass. And to make this easier to read, we are going to flip this. So now mass is on the left. Not really that important of a step, but I just do that because I like to solve or have what I'm solving for on the left side of the equation, just to make it easier to read. From this point on, we're going to substitute in E ESA plus 15 kilo electron volts for E. And I'll explain why we're doing this when we get to the detailed diagram a few slides later. So as you can see here, we have 2 times E ESA plus 15 kilo electron volts over velocity squared. Therefore, there is our equation. So now on the next slide, we're going to continue this. What we're doing here is we're replacing velocity with distance over time. I'm sure you all have learned in school, in physics or whatever class, that velocity is equal to distance over time. So we're basically just substituting in distance over time to what velocity is. This makes it so it's easier to solve. We don't have to have 2 different equations going at the same time. We just have what we want all in one area, or all in one equation. So we're measuring E ESA with the electrostatic analyzer. Again, ESA is electrostatic analyzer, and time, which is T, is measured with the time of flight simulator or analyzer. So the values we know already are distance and the 15 kiloelectron volts. The 15 kiloelectron volts is constant. We know that. And the reason we have this is because when the ions enter the analyzer, we're actually kicking them into the analyzer by 15,000 volts, which is kilo electron volts, 15,000. And that gives it a push into the analyzer so it can get going. So that is why we're taking the value we measure for E ESA and adding 15,000 volts to it, because we kicked it in 15,000 volts. And of course, distance we know because we built the analyzer. So now we have everything we need to know on this side of the equation. So now we can get mass. So here's a more detailed diagram. Again, now you can kind of visualize the ions being kicked into the plate here. So the first step is ions flow through carbon foil A right here, and it knocks an electron out of the foil. Therefore, neutrals are released on the other side as well as the electrons. So before we talk about the neutrals, we're going to talk about where the electrons are going first. So electrons are getting pulled by this surface first, because as you can see, this is the first surface of these electrons encounter. So this surface pulls them to the right. You can kind of think of it like a magnet. So these are being pulled over by these 3 surfaces here, and these are charged with some electron or voltage value. They get pulled down by S2, which is this L-shaped surface here. So they go down here, and now they hit detector number 1, which is this right here, and that starts the timer. From that point on, we go back to the top, and now we're going to see what the neutrals are doing. So when the electron gets knocked out of the shell, the ions turn into neutrals here, which flow straight down. Once they do that, they hit carbon foil B, and again, electron gets knocked out of the foil, and now they're turning to electrons. So electrons head straight down to detector number 2, and that stops the timer. So now we have our T value. At this point, I can talk about the particle time. So I have different variables here signifying different parts of the analyzer. So first off, T3 minus T2, which is the distance here between these 2 variables, is less than 1 nanosecond. So to put that into perspective, we're talking 1 second equals 1 with 9 zeros nanoseconds. So this is happening in like a billionth of a second, almost instant. So from here, we have T1 minus T0, which is the distance between these 2 distances here. These 2, T1 and T0. It's a little bit longer, but because they're electrons, they're so light and agile that they flow nearly instantly. So that time is just about 1 nanosecond. The neutrals are not as agile, so they take a little bit longer to flow between these 2 points here, T2 and T0. So 10 to 100 nanoseconds. So it's a little bit longer, but still, again, this is like a millionth of a second. It's very, very, very fast. So you're probably wondering, well, I see these are being pulled by the surfaces here. Why aren't these being pulled by the surface? And that's because these L-shaped brackets and these surfaces here are charged with a certain amount of volts on them, but that doesn't mean that they're always going to affect the particles that are being flown by them, because these here, the neutrals, have no charge. The charge is basically zero. So because that, following the multiplication identity of 0, anything times 0 is 0. So these surfaces here could have 1,000,000 volts, and then these neutrals are still not going to be drawn towards them because they have 0 charge. Anything times 0 is 0. So they continue in a straight line down to the bottom, which, as you can see there. So conclusion. So I helped design an updated time of flight analyzer used to determine composition of plasmas. I explained the theory of operation of the electrostatic analyzer and the time of flight analyzer. Of course, I visualized the simulation so it's easier for everyone to understand that's viewing it. And most important of all, this is an experiment. It was uncertain whether redesigning the time of flight analyzer was actually going to help or not. And in this case, I almost got it improved, but not quite. And I'll show you that in the live demo in Simion. So let me take a moment and switch the screen over again, and I can show you the Simion simulation.
I'm just going to give you a 2-minute warning, Ben. Is that enough?
Yeah, I'm almost done.
All right.
So this is the simulation here. As you can see, this is basically a rough like redrawing of the services I showed in the presentation. So if I click fly them here, you can see that they go. We're simulating that curved the electrons when they first come out and curve here. So as you can see, I almost got it here. I got these electrons here, about half of them where I wanted them. Unfortunately, the other half ran into this L bracket here. So not quite an accurate simulation, but it's close. And of course, Simion is very sensitive, so adjusting any value, even a few volts up or down, can totally screw with the simulation. So getting this shape took several hours to do. So I'm happy with this progress alone. Unfortunately, I was not able to really simplify the design that much, but that's okay because we did research. We weren't sure if it was going to work or not, and we found this out. So now we've got what we needed. And that is basically it. Any questions?
Thank you, Ben.
Wow, that was pretty impressive.
Thank you.
I'm not even sure I know what to ask.
Anyone out there? Does this presentation speak for itself?
Yes, we'll clap.
We'll clap. I'll throw confetti.
I've got a question.
Go for it, Riley.
Were you previously aware of how Simian worked, or did you learn that over the course of your internship?
I didn't know Simion existed at all, so I completely learned it from the bottom up. Gwen taught me a lot about how Simion worked, and Muhammad explained like the actual math behind it. So they helped me get up and running with Simion. It's very old software, but it still works, the industry standard. So it's always good to know the industry standard software.
That is true. All right, great question, Riley.